When we look at the mean, we are finding the balance point of our data, while the median gives us the physical center, showing us exactly where the middle observation sits regardless of extremes. The mode simply highlights the most popular value in the set, but to understand the noise around that value, we use standard deviation to see how much the data points actually wander away from the average. Variance provides the mathematical foundation for that spread by squaring the distances, whereas the range offers a quick high-level look at the total span between our absolute highest and lowest boundaries. To see the internal structure, we use quartiles to chop the data into 4 even blocks, focusing specifically on the interquartile range to ignore outliers and see where the heart of the data lives. Skewness tells us if our data has a long tail pulling it to one side, while kurtosis describes the peakedness, whether our distribution is tall and skinny or flat and heavy-tailed. Every statistical claim starts with probability, the math of chance. When that chance follows a perfect bell-shaped curve, we call it a normal distribution, which is the foundation for most of the tests we run. Through hypothesis testing, we decide if our findings are meaningful. The p-value is the critical number here. It tells us how surprised we should be by our results if nothing but luck was at play. A confidence interval gives us a safety net by providing a range where the true answer likely sits, while the significance level is the line we draw in the sand to decide what counts as proven. Sometimes we get it wrong. A type 1 error is a false alarm, finding a result that isn't there, while a type 2 error is a missed opportunity, failing to spot a real effect that actually exists. The power of a test is its ability to find those real effects, whereas the effect size tells us if that found difference is actually large enough to matter in the real world. Correlation shows us that 2 things are moving in sync, but we must remember that it doesn't prove causation. Just because 2 patterns match doesn't mean one is driving the other. We use regression to predict the future based on these relationships, but we always check the residuals, the errors, to see how much our model actually missed the mark. R-squared tells us what percentage of the story our model explains, but the quality of that story depends entirely on the sample size. The more data we have, the more reliable our predictions become. To understand a massive population, we take a representative sample. If we do this poorly, we run into sampling bias, where our small group doesn't actually reflect the big picture. Selection bias happens when the way we pick participants skews the results, often because of a confounding variable, a hidden third factor that is secretly influencing everything we see. A control variable helps us isolate the truth by keeping outside factors steady, allowing us to test the null hypothesis, which is the default assumption that there is no interesting change happening. When we expect a specific outcome, that is our alternative hypothesis. To test it with categories, we use a chi-square test, looking for discrepancies between what we saw and what we expected. If we are comparing the averages of 2 distinct groups, we run a t-test. If we add a third group or more to the mix, we switch to ANOVA to handle the extra complexity. A percentile tells you your standing relative to everyone else, while a z-score standardizes that standing, telling you exactly how many steps away from the average a specific point is. The standard error helps us understand how much our sample mean might jump around if we ran the study again, which is especially useful when an outlier threatens to pull the results in a weird direction. Covariance tracks the direction of a relationship between 2 variables, but if our predictors are too similar to each other, we hit multicollinearity, which makes our model redundant and confusing. Heteroskedasticity is a red flag where our errors get bigger or smaller as we move along the scale, whereas homoskedasticity is the ideal state where our error variance stays consistent and predictable. Bias is a systematic tilt in our results that we try to avoid, while precision is about the tightness of our measurements, how often we get the same result twice. Accuracy is the ultimate goal, hitting the bullseye of the true value. In testing, we measure this through sensitivity, our ability to catch positive cases, and specificity, our ability to correctly identify the negatives.